I'm going to say that on this quiz, the single biggest problem people had is not with stoichiometry. It's not with percentage compositions. You know what it is? It's with formula writing. Remember how I said, like, that's a foundational thing? You're building a ladder and you're standing on it simultaneously? That's where most people's problems were. So, I'm so mean that I will give you all your problems on a test with names and you have to write formulas. Ooh. If you can't do the first thing, you can't do the second. I'll give you a few formulas, but I give you most of them with just, here it is. So, let's do the stoichiometry part first. Number 1, what is the mass in grams of 3.75 moles of magnesium hydroxide? First thing you have to do is, well, magnesium forms a 2+ ion. Hydroxide is an OH1 minus. So that would give us MgOH 2 times. If you don't write the right formula for that, you don't get the right mass for it. So I had some magnesium hydrides, I had some magnesium peroxides, I had magnesium oxides, I had all kinds of interesting things. And I had a few magnesium hydroxides. So then we're going to total up the mass for that. Mg is 24.31. Oxygen, of course, is 16 times 2. Hydrogen, 1.01 times 2. And we get a total of 58.33 grams per mole. Now, a word about showing work. You know, I always say, show your work. If you don't show your work, I don't give you credit. There are some pieces of work you don't have to show. Okay? I think you should always show this. It's useful for you as much as for me. Okay? It's a way to not only organize the thought, but it's a way to backtrack if you screw something up and go, oh, I copied the mass for manganese. You know, so it's a little way to trace back your footsteps if something goes wrong. Now, doing a formal crisscross here, you don't have to show that. Now, if it is a naming problem, if that is explicitly what I'm asking you about, you need to show me that if that's necessary. But if it's something where writing your formula is just the first step to doing a larger problem, you don't have to show me that. But if you're not getting them consistently, you probably need to write it down. And at that point, it's not for my benefit, it's for your benefit. I feel really old when I say this. I have been doing chemistry longer than any of you have been alive. Like, my first brush with chemistry was before you were born. Holy crap, and most of you people drive. This is terrible. There are still compounds where if I'm writing a formula name, I write it down. You know, not simple ones. Like, I wouldn't write down magnesium hydroxide at this point in my life. I don't write down ammonium nitrate. Like, there are a lot that I can just kind of flip off my head. But there are ones that have, you know, weirder compounds, bigger charges, whatever. And I would actually, in the margins of my own paper, especially like the transition metals, you know, the copper 2s and the iron 3s and vanadium whatevers, I write those down. And it's just a way to keep track of it. And setting that off to the side is really helpful. So that's just my little spiel about writing it down versus not writing it down. Okay, this part you definitely need to show. The part that's really the crux of the problem, what the problem is explicitly testing you on, is doing stoichiometry. So of course you have to do a factor label. So with any factor label, with any stoichiometry, we always start off with our given. Okay, 3.75 moles of magnesium hydroxide, and we know that we want moles, of magnesium hydroxide down here, and we know that we want the molar mass, 0.33 grams of magnesium hydroxide there. Okay, so when we do the math on this, what do we get? We get 218.7375 grams of magnesium hydroxide. How many sig figs do we have to work with here? 3. So what we have is 219 grams of magnesium hydroxide. Okay. Many people's form was just fine, but their formula was bad. So it's not minor. What it means is that you've learned the second skill, but you still have to learn the base skill. Okay. On number 2, how many moles are represented by 565 grams of iron 2 oxide? Actually, I should have done that first. So, Fe2 plus, O2 minus, FeO. Okay. Iron is 55.85 grams per mole, oxygen 16 grams per mole. We get a molar mass of 71.85 grams per mole. And we're told that we have 565 grams of iron oxide. So we have the molar mass of iron oxide, 71.85 grams of FeO in every 1 mole of FeO. So at this point, simple division, 7.864 moles of FeO. Oh, and I didn't write the raw number in there. It was like 7.8636047 blah, blah, blah. But we have 4 sig figs to work with. So that's our final. Okay. Okay. So the question was, when I do my crisscross, I get Fe2O2. I can do my molar mass from that. You can, but you're getting double the molar mass. This is the simplest ratio, and that's the molar mass you have to use. So you have to use a correct formula, and correct formulas have to be simplified for ionic compounds, not for molecular. But yeah, I had a few people who did that. So not an uncommon mistake, but it'll throw a monkey wrench in your works. Okay. We're asked how many molecules are present in 726.41 grams of carbon tetraiodide. This is a molecular compound. 2 clues. 1, it's 2 nonmetals. 2, I asked you how many molecules. 3, it's got prefixes, so everything points to molecular. So writing a formula, we don't even have to do a crisscross or anything. It's just Ci4, carbon tetraiodide. And we do need to figure out, however, the molecular mass of carbon tetraiodide. And iodine is heavy. It is incredibly heavy, 126.90 grams per mole. And we have 4 of them. So this stuff is like beastly heavy. The molar mass of this is 519.61 grams per mole. Okay. Now, here's the question I have. This one isn't like this one asks how many molecules there are. What are we back to? GMA. Okay. But instead of atoms now, we're dealing with molecules. So you still have to go through moles. So we're going to have to make that middle step a molar conversion. So we want grams of Ci4 here, moles of Ci4 there. 1 mole of Ci4 is how many molecules of Ci4? Six 6.022 times 10 to the 23rd molecules of Ci2 or Ci4. So you have to have this entire setup. You got to go through GMA on this. So many of you remember when doing these, we can take this nice little sort of abbreviated view of the world times 6.022 all divided by 519.61. That whole mess times 10 to the 23rd. The nice thing is that actually works out to a number where you don't have to move the decimal, something that I frequently screw up. So we get this crazy raw number, 8.418700602 something, times 10 to the 23rd. We have 5 sig figs to work with, which carries us all the way back to here. So this is 8.4187 times 10 to the 23rd molecules of Ci4. It's hard to see behind that stupid little hand, but molecules of Ci4. So that's your final answer. Okay, so on the back you were asked to find the percent composition of each element in a series of compounds. For 2 of them, I gave you the formula. For 2 of them, you had to write the formula. Guess statistically across the classes which ones people did better on. The ones where they had the formula given to them. There are lots of chances to trip over your own feet when you're doing formulas. So this one, the formula was given to you, and you just have to separate out all the things that are in there. There are only 3. We have nitrogen with a molar mass of 14.01. We have 2 of them. We have hydrogen with a molar mass of 1.01. We have 4 of them. And we have oxygen with a molar mass of 16.00. Okay, so you don't have to write this part down. I often do, because then you just have to reference back to it. But the total molar mass of this compound is 80.06 grams per mole. Okay. So then it's just a matter, if you've written down that column, this is pretty much done for you. So 24.02 divided by 80.06 times 100, we get, what, 34.9987509%. We have 4 sig figs. This is one of the trickier sig fig problems. We're rounding that based on what comes after it. It's followed by an 8. What does that 9 round up to? 0. And then this rounds up. So the answer is 35.00%. Very few people rounded that one correctly. Those always throw folks for a loop. So it's 35.00% nitrogen. For the hydrogen, we have 4.04 divided by 80.06 times 100. Our final answer, I'm just giving the final, is 5.05% hydrogen. Notice that we only have 3 sig figs for hydrogen because the molar mass sig figs are smaller. So remember, you have to do your sig figs based on what's in the problem, the actual numbers that went into your calculation. Let's shrink that. Let's move these guys up. Okay, and then for oxygen we have 48.00 divided by 80.06 times 100. We get 59.96% oxygen. That's it. Okay, that's the first one. Okay, number 4, you're given sodium sulfate. Many people just wrote the formula wrong on this. So sodium is, of course, Na1+. Sulfite is SO42 minus. So our formula is Na2SO4. If you didn't write the formula right, everything that follows is wrong. So to figure out the percents of all of our elements, we have 22.99 times 2, 32.07, and then of course we've got 16 times 4. So 45.98 and 64. Overall mass of the compound is 142.05 grams per mole. And now we've really got our work done for us. It's just division at this point. Move that. There. I'll stick that up there. Okay. So for sodium, 45.98 divided by 142.05 times 100, we get 32.37% sodium. For sulfur, we have 32.07 divided by 142.05 times 100, we get 22.58% sulfur. And last but not least, we've got one of our favorite gases, oxygen. We have 64 divided by 142.05 times 100. We get 45.05% oxygen. Oops. Okay. Questions, comments, or concerns on that one? Again, I think for the most part, people who missed it because they wrote a bad formula. So, almost everybody got this one. It's a nice, simple one. There are only two things in it, and I gave you the formula. So this was the one that was probably the least missed question on the whole thing. Chloride, 35.45 times 2, 70.9. So our total mass is 110.98 grams per mole. Okay. And so for calcium, 40.08 divided by 110.98 times 100. Illegible Moser, 36.11% calcium. And for chlorine, 70.90 divided by 110.98 times 100, and we get, when we sig fig and everything, 63.89% chlorine. Okay? All right, now on for the most missed question. Allow me to point you to a few resources. So, I don't do the whole memorize the first 20 elements of the periodic table because I think that's stupid. You're going to look it up, you're going to use it. But I also give you a periodic table that doesn't have names written on it. How mean. What you do have, however, are some resources. And for any of the metals, if you look back here on this chart of common ions, you have the name and the symbol. That's helpful, I think. I mean, that's at least... what, 1, 2, it's some number of them where you have a name and a symbol. So I had a number of people who used Fe for lead, and of course that's iron, and so of course they missed it. So if you look on the back, that's a good resource to scan, so don't forget to do that. Okay, number 4, lead 4 carbonate. Okay, lead 4 carbonate. Well, we have Pb 4 plus and we have CO3 2 minus. And again, there's a moment if you're doing your crisscross where it looks like that, but you have to reduce. You have to reduce those ratios. So it's just Pb CO3 2 times. Okay. So once you've got that, you can go ahead and figure out all your masses. And holy moly, is lead heavy. Like every single atom of lead is really, really heavy, which is, completely obvious. And yes, things that have lots of mass per unit volume, in other words, things that are dense, well, they're made of heavy atoms, but it never fails to amaze me anyway. Oh well. Okay, so that's what, 24.02, that's 96, yeah? Yeah. So the whole thing there gives you 327.22 grams per mole. Okay, for lead, we have 207.2 divided by 3, 27.22 times 100, 63.32% lead in this compound. Carbon, 24.02 divided by 327.22 times 100, we get 7.341% carbon. And then we've got oxygen, good old oxygen. .00 divided by 327.22 times 100, we get 29.34% oxygen. Okay? Questions, comments, or concerns on any of the FIP stuff? For the most part, if you made mistakes, do you see where they were? I think for most people the mistakes were largely in formula writing, which I'll go ahead and mention it here. As the chapters go on, the book believes in a ladder-based approach to chemistry skills too. So like those last questions at the end of the homework, increasingly, so like in this chapter, to do the percent comp, you might have to write the formula first. In the next chapter, to do something else, you have to write the formula first and then do whatever. So it's always more than one skill that's being tested. When the bell rings, we go to 7th, right? Okay. What I'll do is we're going to go over one last concept, and I'm going to give you time to ask questions about the homework or work on the homework. Homework is due tomorrow. There will be a take-home FIP quiz. It will be available in this room, second period. Do it whenever you want, and then I'll have the key posted outside the door, and multiple copies made, of course, to prevent whatever sort of mischief we get up to. And it will be on finding empirical formula from percentage composition, and the concept we're going to cover today, which is the relationship between molecular formula and empirical formula. Okay? Questions, comments, concerns? No? Good. We'll stop this.